Okay, we're very happy to have Saeideh Bahrami from the Institute for Research in Fundamental Sciences in Tehran, here to talk about I-small submodels of countable models of arithmetic. Go ahead.
Thank you. Thank you very much. Hello, everyone, again. And let me thank the organizers, especially Roman and Athar, again, for giving me the chance to talk here again. I'm going to talk about I-small submodels of countable models of arithmetic. Let's go directly into the motivation behind the notion of I-small subsets and submodels. It's a long tradition in the study of model theory of arithmetic that whenever we are studying a model of theory of arithmetic, for example, Peano arithmetic or any fragment of this theory, I mean first order theory, we can look at this structure from 2 points of view. A point of view is looking at it as a structure, as a model of the ground theory. The other point of view is looking at that structure as a model of some fragment of set theory. Looking at this structure, and this point of view gives us an insight which helps us to have many fruitful results. For example, in 1970s, Caribbean Paris started to looking at cuts of a model of arithmetic in the way that set theorists look at the cardinal numbers. And by a cut, I mean an initial segment with no maximum element. And it's a tradition in set theory to attribute combinatoric properties to cardinal numbers. In a similar way, we can investigate such properties for cuts, such combinatoric properties for cuts. For example, regular cardinal are corresponded with semi-regular cuts, weakly compact cardinal are corresponding with strong cuts, and by looking this way, we can the most important results that are achieved are independence results, finding first order properties which are independent from the theory that we are investigating. For example, the first mathematical first order property that was found after Gödel achievements was the Paris-Harrington, was by the work of Paris-Harrington. It was about the strongness of standard cut. They found models that in which the standard cut is strong, or and there are some models of Peano arithmetic in which a standard cut is not strong. So for any subset of a model of set theory, we can attribute a cardinality, a cardinal number to that set. We can have the cardinality of that set. In a similar way, when we have a model of arithmetic, a theory of arithmetic, for example, we are working with a theory of I sigma 1. By a theory of I sigma 1, I mean the fragment in which the induction scheme is restricted to sigma 1 formulas. And from now on, whenever I'm talking of M, I mean a model of I sigma 1. And whenever we have a cut of M, which is an initial segment with no maximum element, a subset of M, like EX, is I small, whenever from point of view of the structure M, X has the cardinality of I, or to be more exact, there exists some function, some coded function in M whose restriction to I is a bijection from I into X. And since we are working in the theory of I sigma 1, we can talk about sequence numbers. So equivalently, X is I small. Whenever we have an element in M which codes a sequence such that the restriction of that sequence to I is equal to X, and the restriction of sequence is 1-to-1. And whenever we are using with the standard cut, we simply say small instead of small. And the first appearance of small submodels was in a paper by Lascar in 1994. In that paper, he wanted to investigate if the automorphism group of countable recursively saturated model of PA has a small index property or not. For this purpose, he wanted to simulate a method that was used before in set theory, and he needed the notion of he needed the submodels of the ground model with smaller cardinalities. But here in models of Peano Arithmetic, we didn't have such models, such submodels. So he introduced the notion of small submodels. My plan is to, first of all, I'm going to investigate some properties of I small submodels of M. And then I'm going to recount some results about automorphism group of countable recursively saturated model of PA and the relation with I small submodels. And then I'm going to generalize these results about automorphisms to initial self-embeddings, which I'm going to define what I mean by an initial self-embedding. So first, let's see
Saeideh, can I ask a question much earlier?
Yes, sure.
Really just from the very intro of the talk, you have this association between these notions from set theory and notions of cuts in arithmetic, and I wanted to know if you could just say a little bit more about how that association is or that analogy is how does that actually, how do we actually understand that analogy? In what sense is a cut in a model of arithmetic analogous to a cardinal, or a semi-regular regular cut being a regular cardinal? That's
Pardon. As I mentioned, a cut is an initial segment with no maximum element. So it, from the point of view of the model, it cannot be in a bijection with any initial segment or with any not with any initial segment. It cannot be in there couldn't be any coded function between the a cut and any finite initial segment from the point of view of model. In that in this sense, it is that this notion is similar to a cardinal number. I don't know if that answers your question.
I see what you're saying. Yeah, thanks.
Yeah, and when by a similar let me come back here. We have the regular cardinals are those cardinals whose cofinality is is equal to the cardinal itself. This property can be said in the first order formula, first order sentence, and it can be attributed to a cut from the point of view here, from the point of view of the model. Here, every function, when we are talking about cofinality, when we want to talk about the function of the cofinality, we want the function to be coded, and we want that function to be a bijection from the cofinality to the cut itself. And whenever we're talking about strong cuts, we mean a kind of infinite Ramsey theorem should be satisfied in the cut. I'm going to talk about strong cut in the coming slides more.
Okay.
I hope.
That was great. Thank you.
If I may add something,
Sure.
Athar, another analogy was with, if you think of weakly compact cardinals, the stronger the combinatorial property on the cardinal, the stronger the theory that's satisfied by V kappa. So there was a link there between the set theoretic properties and the arithmetic properties.
Mm-hmm.
Thanks, Larry.
Thank you. First of all, let's see which subsets of M, the structure M, can be I small. Trivially, I itself is I small, and whenever we have a submodel, I small submodel like M0 of M, such that I M0 contains I, so trivially M0 shouldn't is not cofinal in M, since A is an upper bound. Moreover, it is not M0 cannot be an initial segment of M. Because when we are working in a model of Y sigma 1, we are facilitated with Ackermann's membership relation. Here, Ackermann membership relation, which is denoted by this formula E, which is a delta zero formula, is very similar to the membership relation in set theory, in models of set theory. And whenever we are talking about a member of M, and whenever A is a member of M, by A we mean E members of A. So we have I standard system of M, the notion of I standard system of M. And whenever we have an indexation of M, the index and extension and M should have the same I standard system. It is easy to prove this fact. So if M0 is an initial segment of M, it has to have the same I standard system to M. But it is not the case, because if we let A be the subset of A, the subset of I, which is defined like this, the definition is very similar to Russell paradox. This A is not empty because we have a zero. Zero is the number zero is in M0, and number zero E members is empty. So, and it is delta zero definable, so it is inside I standard system of M, but it is not in the same way that we prove that the Russell set lead to a paradox. In the same way, it cannot be in this I standard system of M0, because any member of M0 is like this. So
Saeideh, I'm a little bit confused here because what if M0 is the same as I?
Sorry?
Oh no. You know, what if M0 itself could be M0 small?
I said I is a proper subset of M0.
Sorry. This is what I missed.
Yeah.
Thank you.
You're welcome. Whenever we have M by an easy compactness argument, we can find some elementary elementary extension of M in which M is small. And to continue investigating the property of I small, I need here to open the parentheses and fix some notation together. Whenever we are working in a model Y sigma 1, we can code every delta zero formulas and we can canonically enumerate all of these delta zero formulas. Note that these formulas can be non-standard, but we can enumerate them in a canonical way. What do I mean by a canonical way? I mean that whenever one of these delta zero formulas is standard, the Gödel number of these delta R is equal to the index of equal to this R, to the index of delta R. We can do this in a model Y sigma 1, and fortunately we have the satisfaction predicate, truth predicate for delta zero formulas, and this is delta 1 definable. And these are some notations for every R in M. Whenever I'm talking about if R of X, I mean the sigma 1 function which is the least element such that this property holds in for that. And whenever I'm talking about this notation, if R of X diverges, it means that it is for just for abbreviation. There exists some z and y's such that delta R of X and YZ holds, and this one is when we bound the quantifiers by W, and the italic F is the collection of all empty definable partial sigma 1 functions. So now we can close the parentheses and go on. So whenever we have an element in M like C, all of sigma 1 definable elements of M which are defined with C as a parameter are which is denoted by this K1 of M and C is small in M. It is easy to prove this because K1 of M and C is equal to these all of the elements of this subset is equal of this kind. So we can find some member in M which codes a sequence such that all of its members is these elements. And they might be repeated in the process of making this sequence, but it doesn't matter because this subset is infinite, so we can omit the repeated ones, and after eliminating all the repeated one, again we have an infinite subset, so we can find so we can get rid of all those of repeated ones, and we can have a sequence number whose restriction to n the standard card is equal to this K1 of M and C. But whenever we talk about K1 of M and I, when I is a cut, the parameters here come from this cut I. Here, it is not that easy to get rid of the repetition like this. As a result, we need the notion of strong cut here. By strong cut, I mean that these combinatoric facts holds. This is those are who are familiar with Ramsey theory know what this is a combinatoric fact that says that if we have a function from in to a, I should have a homogeneous subset. But here we work with the equivalent definition, which is more model theoric and which is more useful to us. This equivalent definition says that whenever we have a coded function whose domain contains I, there exists some element E in M such that the interval between I and E is void of any of these Fi's, such that I is in I. So, when I is small, I is strong, we can show that K1 of M and I is I small. The proof is similar to the previous one. We can find some A which codes which codes a sequence whose restriction to I is equal to a K1 of M and I. But here we have to make this sequence to be one-to-one. For doing such a thing, we define this delta zero function here, G. We enumerate elements of I one by one in a linear order. We take A0 to be the first element and to be the first one. Then we have A1, then we have A2, but we, in a way that if A1 is equal to A0, we eliminate that, and we put J1 to equal to A2. So for inductively, we define that Gx plus 1 is the first AR equal to AR, such that R is the first one, such that AR is not repeated before. And we put H to be the function, the definable function that defines the index of that G. So since I is strong, this property holds for H. We have some E that this property holds for A. And my claim here is that if we name this subset M0, this M0 is a subset of GI. If any AI is equal to some GJ such that J is smaller than I. But we cannot make sure that if M0 is equal to this GI. This I have tried to make the figure that what's going on here. This M0 is a subset of GI, and this is the cut I. But they might be some element of GI which are not in M0. If suppose that GI0 is not, so I0 is in I and this is not in M0. So by the definition, HI, the index of GI should not be in I. So by the strongness, it has to be larger than A. So suppose that I0 is the smallest one with these properties, that HI0 is larger than A. As a result, M0 should be equal, because A0 is the smallest one with this property, M0 should be equal to JI's, such that I is less than I0. And this is a contradiction because this makes M0 to be definable in M, which is not, which is delta zero definable, since G is delta zero definable. So M0 is equal to GI, and this and G. Sorry, I forgot to note that this G by definition is 1-to-1. As a result, the restriction of G to I is the bijection from I to K1 of M and I. Whenever we have a countable recursively saturated model of PA, Kozak and Schmer proved that there exists some small recursively saturated elementary submodel M0 of M. So it has 2 to the Aleph 0 many elementary submodels. With a similar strategy of their proof, we can prove that there exists some recursively saturated I small elementary submodel of M0, I small M0 of M, and in particular M0 cannot be of the form of K of M and I because this one is not recursively saturated.
Saeideh, so is this for M that's a model of PA or I sigma 1?
Yeah, no, for a model of PA, and it has to be recursively saturated.
Right, for the second result as well.
Yeah, for the second result as well. And I don't know if it is a model Y sigma 1 in the result holds or not. And since we have a recursively saturated model and it is countable, so we can find a satisfaction class for M such that the expanded model is also recursively saturated. So we can put M0 to be, for the first one, we can put M0 to be equal to the definable elements of expanded model. This one is, by a similar argument, we can prove that this one is small in M, and it is recursively saturated because S intersection with M0 is a satisfaction for K of M0. For the second part, we can put M0 to be equal to K of M0 and I union A sum A such that A is not in I. We need these to prevent that M0 to be equal to I. In a similar way, we can prove that this is I small and it is recursively saturated because S intersection with M0 is a satisfaction class for this one as well.
Are we assuming anything about I here? Is I still strong or?
Yeah, I's for I'm going to talk about 3 properties for I, and in all of these 3 properties I should be strong. Here is the second property, and this one is the third one. Here again I is strong.
I'm sorry, could you remind me what small means in the Cossack-Schmel?
They have the same definition. They say that a submodel is small if there exists some sequence number whose restriction to n to the standard cut is equal to that submodel.
Oh, right. So it's just I small where I is the standard cut.
Yeah.
Thank you.
Yeah, you're welcome. And this result is essentially to NIH, which says that whenever I is strong, whenever for every I small submodel M0 of M, I should be inside a subset of M0. So suppose the proof is like this. Suppose M0 is equal to this sequence, and let X be this subset of Y. Here, this definition is the pairs of elements of M0 with their indexes. This is inside I standard system of M. But if it is assumed that, if we suppose that I is not a subset of M0, so I and the expanded structure I and X should satisfy that there exists some X such that for all Y's, Y and X cannot be in X. And since I is strong, because every strong cut is a model of PA, and when we add the elements of I standard system, the expanded structure is also a model of PA. So A and X should be a model of PA, and it is a model of I sigma 1. So it's there must be some X0, which is the least one with this property. But if AX0 is the least one with this property, it is not in M0 and it is not equal to 0, because 0 is 0. So X, that's a contradiction. Everything collapses. And so here we saw that I didn't use the whole power of PA. I just used I sigma 1. So for this statement, I doesn't need to be strong. It just if it is semi-regular, we just need that I and X to be a model Y sigma 1. So if it is semi-regular is enough. But I don't know the answer to this question, if the strongness of I is necessary for the two other statements that I said. I don't know if it is necessary or not. Let's turn to the automorphisms. For this part, we suppose that M is a countable recursively saturated model of PA, and in a famous paper by K. Kasakatlarsky in 1991, there is a result that which says that whenever we have such M, a cut of M is strong, and it is an elementary submodel if and only if there exists some automorphism J such that fix of J is equal to I. Then they say, in that paper, they say that Schmerl has said that the same result holds for all I small submodels. The proof is similar to the case when M0 is equal to I. And afterwards, in a paper in 1995, Kasak and Schmer proved that for every small elementary submodel M0 and every automorphism, the intersection of M0 and fix of J is also small in M. And in the same paper, they find some equivalent statement with the strongness of a standard cut. They say that they prove that for N is strong if and only if for every small elementary submodel there exists some J. This is actually this theorem is a special case of this theorem. The third statement says that there exists some automorphism J of M such that fix of J is a subset of M0. Here, by this notation, I mean the initial segment generated by the definable elements of M, K of M. And the fourth statement says that there exists some automorphism J of M such that fix of J is not equivalent to M. In the next part, which we are talking about initial segments, we are going to prove to generalize all these two theorems about for any model of Y sigma 1, any non-standard countable model of Y sigma 1. We don't need recursive saturation, and we substitute automorphism with initial self-embeddings. And then also for these results, we have a generalization for initial self-embedding. This result is about extendability of automorphisms. When we have a small elementary submodel, and if J is an automorphism of M0, then we can extend the J to the whole model if and only if there exists some B in M such that this property holds, and the same holds for the J inverse. And in 2006, NIAT proved that Schmer result, not only whenever we have an I small elementary submodel, not only just one automorphism exists, but 2 to the aleph 0 many of those automorphisms exist, such that the fixed point of them is equal to M0. Now let's see let's see the generalization of these theorems for initial self-embeddings. First, let me say what do I mean by an initial embedding. In 1973, Friedman proved a remarkable theorem that says that whenever we have two countable non-standard model of PA, the necessary sufficient condition for embedding M into N in a way that J of M, the image of J, is an initial segment of N, is that they have the same standard system and they have the same sigma 1 theories. By an initial embedding, I mean such an embedding that whose image is an initial segment of the codomain. And whenever M and N is equal, it is an initial self-embedding. After Friedman, there were many refinements of his theorem, especially Rosser proved a similar result for models of I sigma 1. And in his results, he talked about how whenever M and N is equal, how J fixes points elements of M. And then we have a similar version for models of Y delta 0 plus X. Here has some details. M and N needs to have some needs to be recursively saturated, or one needs to be one tall, the other needs to be one extendable. But we are not going to go to details of these to this version of Friedman. We just use it whenever we need it. In 2018, NIAT and I proved that whenever M is a model of I sigma 1 countable and non-standard, I is a cut of M, I is strong in M and a sigma 1 elementary if and only if there exists a proper initial self-embedding J such that fix of J is equal to I. And whenever M and N is strong in M, if and only if there exists some proper initial self-embedding whose set of fixed point is as minimum as possible. But we can refine this theorem, not just for I and N, but for whenever we have a I small sigma 1 elementary submodel of M, then we can prove that I is strong in M if and only if there exists some proper initial self-embedding such that the set of fixed point of J is equal to that M0. So these two are a special case of this one. Here I'm going to say a little about the proof of the from left to right direction of this theorem and the idea behind the back and forth here. So we assume that I is strong in M, and we want to find some proper initial self-embedding J of M with this property. Since we are working in a model Y sigma 1, we have some restriction. As a result, we need to work first in these structures. Let me introduce what I mean by this notation. Whenever we have a subset of X of M, by I1 of M and X, I mean the initial segment generated by K1 of M and X, which is a sigma 0 elementary submodel of M. It is not a sigma 1 elementary submodel of M, and it is not sometimes it is not a model Y sigma 1 most of the times. So we repeat this process. We again take K1 of this I1 of M and X and generate initial segments of it, and iterate this process to have these in this initial segment. Finally, we can see that this initial segment is a sigma 1 elementary submodel of M, and it is a model Y sigma 1. So now we are ready to construct that J, the initial self-embedding J that we wanted. First, instead of building an initial self-embedding of M, we build an initial self-embedding of H1 of M and M0. I will mention why we build an initial self-embedding of this H1 instead of M itself.
Saeideh, can I ask you, sorry to interrupt. So are there some analogs for N rather other than 1? Would it work the same for?
Yes, yes, we have the same.
So you'll say something about it, will you?
Yeah, yes, it's Hayek and Pudlak book that for every N we can define such structures, and this is a model Y sigma N, N plus 1, and this is a sigma N plus 1 submodel of M, and this has nicer properties than this one, because this one is always, whenever we have N instead of this one, it is a sigma, it is sigma N, it is sigma N elementary submodel, not sigma N plus 1.
Yeah. All right, thank you.
Okay. So we will construct some alpha. So the main ingredient of the proof is constructing this alpha. We will construct some alpha such that the fix of alpha is equal to M0, and some B, we can find some B, which is the upper bound for the image. Then, since this submodel is a model Y sigma 1, and it is an initial segment, so it has the same standard system, I standard system with M, and it is a sigma 1, it has the same sigma 1 theory, so we can use I sigma 1 version of a Friedman theorem, and we can find some beta, such that beta fixes any elements of M0, and this upper bound is in the image of beta. As a result, we can, since this beta is in the image of beta, and it is an upper bound for the image of alpha, so we can talk about this, and this is an initial, this is a well-defined initial self-embedding, and it is easy to see that the set of fixed point of J is exactly equal to M0. So the main part is constructing this alpha. In order to construct this alpha, we work, our method is back and forth. First, let's fix some B, because we have a strong sigma 1 collection in H1 of M and M0. We can find some B, which can serve as an upper bound for the image. So we want to inductively build finite functions of functions u into v, such that of elements of h1 of m and z, such that these such a two property holds. The first property is this p of u and v, this u and v, for all I in I and for all sigma 1 partial for all partial sigma 1 definable functions. This property says that guarantees that these finite functions are embeddings, and B is an upper bound, and they fix all of elements of M0. So we need another property which guarantees that any element which is not in M0 wouldn't be fixed. It would be the image of any element which is not in M0 by alpha would not be equal to that element. Note that both of these properties are whenever we fix I and F, this property is pi1 and the other property is pi1 as well. Why it is pi1? Since we can get rid of this, it's enough to get rid of this part. And it's easy to get rid of this part because I is strong, and this says that we want that f of u and ai not to be in M0. So we define a subset R of I, which says that f of u and ar is in M0. It says that there exists some k and t in I such that f of u and ar is in the form of some f of t of u and a k. This says that if f of u and ar is not in this R, means that it is not in M0. Since this is a pi1 definable, this R is a pi1 definable subset of H1 of M and M0, so it is coded. So we can use the code of this R in this formula and get rid of this part. So this would be a pi1 formula. So let's see how we do in the fourth levels. Fourth levels are, as usual, for making the domain of alpha to be equal to H1 of M and M0, and back levels are for making the image to be an initial segment. Suppose we have constructed U2 into V, U bar into V bar, and M is a new element in H1 of M and M0. Here, when we have a new element, here the point that we are working in H1 of M and M0 instead of M. Because any element in here has a bound, has an upper bound, whose by a term, we have a term, sigma 1 definable term, such that M has an upper bound like this, T of U, and an element in M0. So it makes, whenever we are working in models, in this model, everything would be bounded, and we get rid of unbounded elements. So we can easily define new functions, new sigma 1 function, because we want to define new functions, and it is important that they are sigma 1. It is important to make the quantifiers bounded. So in order to find some image for this M, We define this set of formulas. Let S be an arbitrary element in H1 of M and M0, and we define this set of formulas that says that y as a free variable would be less than this, because the M is less than this term. And for every I and I prime, P, the two properties that we wanted hold. So if we find some S, some element smaller than I, such that this type is finitely set, we can call this set of formulas type, it is that means it is finitely satisfiable, because all of these formulas are pi1 and it is bounded. So, and we are working in a model I sigma 1, so it would be realized in H1 of M and M0, and any realization would serve as an image for this M. So we are searching for such S, which is fine, which makes PS of Y finitely satisfiable. In order to this, we define a delta zero function, which says, intuitively, what it does, this function says? It says that g of x is the largest S. This B here is for making it bounded. The largest S such that PS of Y is satisfiable for all elements FR, such that R is less than X. So, because this is delta zero definable and I is strong, we can use the strongness of I and find some E such that this property holds. And our claim is that PE is finitely satisfiable. How do we prove this claim? We have a lemma here, which I'm not going to go through the details of the proof of this lemma, because I think this is a little time-taking, and that would make the talk boring. But I added some slides at the end of the talk, and I can send the slides to Atar or Raman, and who is interested in the proof of this lemma can see what is the idea of the proof of this lemma. This lemma is says that for any finite elements of F that we have, there exists some S larger than I, such that this property holds. The proof of this lemma is by contradiction, and we define some new functions, some new sigma 1 functions, and we use the induction hypothesis and gain the contradiction. But we want to use this lemma to prove that PE, the type PE of Y, is finitely satisfiable. First of all, note that since the type PE of Y has two parts. One part is this for the property P. The other part for the property Q. But for this part, we don't have any problem, because by Friedman theorem we can find some Y which serve as an image for M. So the only part is the Q part of the type. So we can just fix one F for the P part of the type, and take any number of finite elements of F. Then by repeating this lemma as many as possible, for example, k prime many times, such that k prime is larger than the number of these elements, and it is larger than the Gödel number of this f, we can repeat the lemma k prime many times, so such that the property holds for every fr such that fr is less than k prime. This lemma holds for all of these frs. So we will find some s at last. We will find some s which is larger than I, and lemma holds for all of these frs. This means that by the definition of g of k prime is larger than s, so it is larger than I, so by the strongness it is larger than E. So since E is smaller than g of k prime, and g of k prime was the largest one, such that p of y is satisfied for these elements, so it is satisfied for these elements. And this finishes the proof of the theorem. Let's turn to the standard cut. When we have the standard cut, similar to the case when we had the automorphisms, we can find some equivalent statements with the strongness of standard cuts. So n is strong if and only if for every small sigma 1 elementary subset there exists some proper initial self-embedding such that the equivalence of f1 and 2 is a special case of the previous theorem. And statement 3 says that there exists some proper initial self-embedding J of M such that fix of J is a subset of I1 of M. I1 of M is the initial segment generated by the sigma 1 definable elements. And whenever M is a recursively saturated model of PA, all of these three statements are equivalent to the fourth one, which says that there exists some proper initial self-embedding J of M such that fix of J of M is a model of sigma 1 collection, and it is not isomorphic to any initial segment of M. I don't know how much time do I have. I think
you can continue. How much more time do you think you need?
I think I can finish it in less than 10 minutes.
That's more than enough. Yeah, that's more than fine.
Okay. Okay. Thank you. So let's see the idea of the proof of this corollary. Here, the equivalence of these two is a special case of the previous theorem, and the direction from 1 to 3 is also a special case of the previous theorem. We just need to prove the direction 3 to 1 and the equivalence of 4 to these 3. So suppose we have 3. At the recall that at the beginning I said that whenever we have a model of recursively saturated model of PA, Kazak and Schmerl proved that there exists some proper Oh, sorry. It is I'm proving 3 to 1. From 3 to 1. So suppose that there exists some proper it says that there exists some proper initial self-embedding J of M such that fix of J is a subset of I1 of M. And we want to prove that N is strong in M. First, there exists some element B in M, which is not in I1 of M, because I1 of M is not a modelable collection. But M is a modelable collection. So suppose N is not strong. There is a lemma that says that whenever N is not strong in M, by using the witness of the non-strongness of N in M, we can find some C in fix of J, such that the sigma 1 theory of B is a subset of, for any element, we can find such C. Sigma 1 theory of B is a subset of sigma 1 theory of C. So here we can find some C like this, but this C is in fix of J, so it is in I1 of M, so it is less than a definable elements of M, but B is larger than any definable element. So N cannot be, N has to be strong in M. Now for the direction 2 to 4. Direction 2 to 4, let's us take a look at the, here 2 says that for every small elementary, for sigma 1 elementary, there exists some proper initial self-evident J of M such that fix of J is equal. And we want to find some J of M such that fix of J is the model of B sigma 1, and it is not isomorphic to any proper initial segment of. Okay. Now, the thing that I said in the previous slide, recall that when I was talking about properties of small submodels, I said that when Kozak and Schmer proved that whenever we have recursively saturated model of Peano arithmetic, there exists some small recursively saturated elementary submodel of M. So by statement 2, there exists some proper initial self-emitting J of M such that fix of J is M0 because it is small and it is elementary submodel. This J would serve as a witness for statement 4 because it's here M0 is recursively saturated, so it is a model of B sigma 1. B sigma 1 here is the collection axiom for sigma 1, and M0 cannot be isomorphic to any proper initial segment of M because we proved that for any small subset, small submodel, it cannot have the same standard system as M. So so it can, by Friedman theorem, it cannot be isomorphic to any initial segment of M. And for the proof of 4 to 1, suppose statement 4 says that there exists some proper initial self-emitting J of M such that fix of J is the model of B sigma 1, and it is not isomorphic to any proper initial segment of M. We want to prove that N is the strong. Suppose N is not strong. By the previous lemma, for every A, we can find some B in fix of J such that they have the same sigma 1 theories. So they have Ackermann set of A should be equal to Ackermann set of B intersection of N by N. So as a result, they have the same standard fix of J, and M have the same standard system. Moreover, fix of J have the same sigma 1 theory with M, and it is the model of B sigma 1. So the conditions of I delta 0 plus X version of Friedman theorem holds. So there would be a proper initial self-embedding from fix of G into M, which contradicts 4. So N should be strong in M. And the last theorem is about extendability of initial self-embedding. Whenever we have a model of I sigma 1 countable non-standard and M0 is I small and I is strong, and J, if suppose a J is an initial self-embedding of M0, such that an extra condition holds here. J of I is an I said that J is an initial self-embedding of M0, but there's no guarantee that J of I is an initial segment of M. So we have to add this part here. So the sufficient and necessary condition for extending J to some proper initial self-embedding of M is that we have some B in M such that this property holds for J, and moreover, J fixes any elements of I standard system of M. And if these two property holds, by back and forth argument, we can build J and in proper initial self-embedding of M. And this is the criteria for extendability. And thank you very much. Thank you. And I'm sorry if the proofs were boring or time-taking. And I have added as I promised, I have added the proof of lemma here, and I can send these to Atar. Thank you very much.
Thank you.
Okay, thank you. Let's thank our speaker. And I'm happy to open up for questions from anyone. So feel free to unmute and go ahead.
Well, if to just jump in first, I have a sort of a high-level question of a kind. This is, very, very beautiful work, and the starting point was given as, ideas coming from set theory and then going into the model theory of arithmetic. And then, you had the Paris-Kirby work, Paris-Harrington work, had all these things that exploited that connection and gave us a lot of great mathematics. But now this has been carried much, much further and down into details. Now, the sort of original wave of work was sort of mapped back into set theory. There were theorems that characterize, say, inaccessible cardinals using a variation of the notion of large finite set and Ramsey's theorem. But what about these finer analyses you're doing now? Has there been projection back into set theory of any of this work so far?
I know that I see Zach is between the audience. I know that Ali and Zach have a paper on initial self-embeddings of model of set theory, and they have proved similar results for not for I small ones, but for they have similar results like this one. And I am aware of work of Paul Gorbo. I'm not sure if I'm pronouncing his name correctly. He has on his dissertation, he has worked on initial self-embedding of models of set theory. these are the works that I'm aware of.
Mhm. Oh, thank you. Very interesting.
Thank you so much.
Any other questions or comments? Oh, go ahead, Ram.
So this might be somewhat technical, but I do not quite remember all the technical details of the results you were talking about models of PA. But I remember that part of the motivation for studying these extendability questions were all kind of questions about automorphism groups of initial segments, and then how these automorphism groups, so the fact that you can extend certain automorphisms to an elementary end extensions later had some applications. But there was one question that we're thinking about that got never resolved, because you have those criteria when a given automorphism can be extended to a given extension, and there were some obstacles when this cannot happen. So we have some similar thing here with those self-embeddings, but we're thinking of identifying some automorphisms, not those that are extendable, but those that, so the extension is not given yet, but you have an automorphism of an embedding that cannot be extended to any elementary end extension. And we never got very far with it. This is still an open problem in the case of PA, whether there are such when you have an recursively saturated model of PA, and this elementary end extension would be some variant of that, somehow solvable by the techniques that you have here for models of I sigma 1 and embeddings.
I'm not sure. When I was working on this stuff, I was working on a question that Ali proposed. The question was that if there is an automorphism, if we can find some model of I sigma 1 which poses an automorphisms which cannot be extended to any model. That was the question that I was working on, but I finally I couldn't prove that. But recently I have found some theorem in a paper by I'm not sure about the name, Shohat. I found a theorem in that paper that I think that the proof of that theorem can be modified for proving Ali's question, to answer positively Ali's questions, I think.
That would be very interesting. So Erez's results are, both of them are about short recursively saturated models, and that would be very interesting. So let me know when this happens.
Sure.
Okay. Anything else? Okay, let's thank Saeideh again. Thank you, Saeideh.
Thank you.
And we will be off next week, and then we return in 2 weeks back to our usual time, the later time, with I believe Mateusz Welik from Warsaw will be speaking. Is that right? Is that him in 2 weeks?
Right. So Mateusz will be in 2 weeks. Mateusz solved a problem of Montalban and Roseger,
yes,
that Dino was talking to us about a year ago. So that could be something interesting. And if I hope you can all tune in also on December the 12th. So Karol Hrbaczek will be talking about some axiomatic systems for second order, not for second order, for infinitesimal calculus or non-standard analysis. But he will also tell us a little bit. There is a recent beautiful result of Ren and Jin about a proof of Semerelli's result on arithmetic progressions that uses non-standard analysis, and the proof apparently is much simpler than other known proofs, and they use 3 levels of non-standardness. So that will be December 12th.
Very nice. So we have 2 more, as Roman mentioned, 2 more coming up. So please come back to those. Thank you all.